In this screencast I'm going to look at the residue theorem, and I'm going to apply it to the following problem. We're asked to evaluate the integral of the function e to the z divided by z to the 4 minus 1 with respect to z. It's a contour integral and it's evaluated around the circle, centre, the origin, radius 2. Now, in order to proceed, and I'll give you the residue theorem in a moment, the first thing we do need to do is to evaluate the residues of this function. I'll just write it out again. E to the z over z to the 4 minus 1. We need to evaluate the residues at the singularities of this function, and I hope you can see that these are where z to the 4 equals 1, i.e. we're looking at plus or minus 1 plus or minus I. So we need to evaluate the residues of f of z at those 4 points, and I'll do each one in turn. Now, in order to do this, the simplest thing to do is to use what I would call the g over h rule, and that says that if f of z is a quotient of one function of z divided by another function of z, and if those functions g and h are analytic at the point that we're interested in, so at each of our points plus or minus 1 plus or minus I, if g and h are analytic there, and if h at the point we're interested in is 0, which it will be if we're looking at a singularity, and if the derivative of h at that point is non-zero, then in fact the residue of my function at the point alpha is given by g of alpha divided by h primed of alpha. I'll just scroll down a little bit. So that's what I would call the g over h rule for evaluating these residues, and therefore I can apply that in our case because h of z is z to the 4 minus 1, h primed of z is 4z cubed, and I hope you can see that that is certainly non-zero at the 4 points that we're interested in. So what I can now do is look at each one in turn and evaluate. So if I first of all look at the point 1, that's going to be g of 1 divided by h primed of 1. G of z has disappeared off the top of the screencast, but if you remember the numerator, the function was e to the z. So in fact what I'm going to have here is e to the 1 over 4 times 1 cubed. I've just got a quarter of e. And that's the residue at that point alpha equals 1. If I do the same for all of the others, because we're going to need them, what I get for the next one is e to the minus 1 over 4 lots of minus 1 cubed. So that's going to be minus a quarter e to the minus 1. I also have to look at I, and probably the easiest thing to do here is to multiply top and bottom by I, so that I actually get I to the 4 on the bottom, which is just 1. And finally I'm going to get e to the minus I over 4 times minus I cubed, and hopefully you can see that what I'm going to get there, if I times top and bottom by I, I'm going to get a negative sign. So I'm going to get that. So what I've done is found the residues of the function z at the 4 singularities, at the 4 points where its denominator is 0. What I can now do is use those in order to answer the original problem. And if you remember what the original problem was, I'm being asked to evaluate the contour integral of my function around this contour. It's the circle, centre, the origin, radius 2. And what the residue theorem says is that this integral is, or in general, the integral of f of z dz is equal to 2 pi I s, where s is the sum of the residues of f at any singularities that lie inside the contour, provided the contour does not pass through any singularities. So what we've got is a circle, radius 2. I'll just draw this here. And I hope you can see very clearly, if I'm looking at, this is an Argand diagram, that all 4 of my points lie inside the contour, and none of them goes, the contour does not go through any of them. And therefore, in order to evaluate the integral, all I need to do, and I'll just write it out again, is sum up all those residues that I've found already. So what I have is 2 pi I, and I sum up, and I've written them down, but you might have to scroll up to see what they are. If you've forgotten, I'm just copying them out from before. Now we can tidy this up quite considerably actually, so I may as well do that. The first 2 of these, so these 2 here, what I'm going to be doing is using the result that shine of something is e to the something minus e to the minus something all over 2. So what I have in my first bracket is actually a half of e to the 1, I can put a 1 up here, minus e to the minus 1 all over 2. So that is shine of 1. And what I have in the second term is I've got a half I, and then I've got shine of I. You may have to stop this screencast for a moment to check that you're happy with that, but I've used the result in red, the definition of shine of x, in order to simplify. So I can obviously cancel the 2's, which I shall do now. And then I'm going to use one final result in order to simplify further. Now, the way I remember this is that I sine x equals shine ix. And what I actually have here is an I in front, but I can deal with that separately in a moment. So I think I'll use that result directly. And what we have is I, and then shine of I, I'm using my red result with x equals 1. So this is going to be I sine 1. So in other words, I have replaced shine of I by I sine 1. And therefore what I have, because I squared is minus 1, is that as my final answer to that contour integral. Pi I times by shine of 1 minus sine of 1.